Okay, section number 3 is entitled the integral test, and actually the P-series. Now, we have this theorem, this major theorem for this section. It says that if f is a positive function, if f is positive, continuous, and I guess decreasing, and decreasing, then the following is true. But it has to be decreasing, I bet, for x greater than or equal to 1. And the terms of their sequence is the same as f of a. Then the summation of an, and I guess the integral from 1 to infinity of f of x dx, summation of n goes from 1 to infinity. Both diverge or converge. They both converge or they both diverge. And we can do a couple of problems like that. If you have the summation and then goes from 1 to infinity of 1 over n plus 1. What you need to do is look at the integral from 1 to infinity of this, but with an x. 1 over x plus 1 dx. That's just ln of x plus 1. After all, the derivative of ln of anything, you put the anything in the bottom and the derivative on top. So we got back the original function. And now we have to go from 1 to infinity. But, if you get full credit on your exam, homework, what have you, you really can't plug in infinity. So you have to take the limit as k goes to infinity of ln of the absolute value of x plus 1 from 1 to k. Now, this is a very advanced step. If you go into advanced calculus here, if you take advanced calculus, which is actually next semester for you guys, you will learn that you can interchange the limit and the ln. You can't do it with just any old function, but with ln you can do it. Not only will you learn that in our advanced calc, but you'll see the proof of it. Okay, so why don't I do what I just said? Interchange it. So for this semester, it's a rule that you can do. So now you have the limit as k goes to infinity of x plus 1 from 1 to k. And this is equal to ln of the limit as k goes to infinity. First we plug in k, we get k plus 1 minus, then we plug 1 in, we get 2. So we get ln of the limit of k minus 1. But the limit is going to be infinity. So now you have ln of infinity, which diverges. Since the integral diverge, that implies the summation of 1 over n plus 1 also diverges. They're both going to have the same answer. This summation and this integral. Okay, but I did make one, I won't say I made a mistake, but I did do one thing that was a bit sloppy. I never talked about f of x being positive, continuous, and decreasing. Okay, so what I did is all correct, but possibly I was lucky. Maybe my f of x did not live up to the criteria of using this theorem. You can only use this theorem if the function is positive, continuous, and decreasing. So we'll hold off on my conclusion. My conclusion may not be worth anything because f of x may not have been a candidate. 1 over n plus 1 may not have been a candidate for this. So if it is, we're going to assume that f of x is 1 over x plus 1. And we're only talking about x greater than or equal to 1. Okay. Now, okay, that's a comma right there. Let's make it a colon. Now, the thing is 1 is always positive, and if x is at least 1, then x plus 1 is positive. It's 2 or more. So the bottom is positive. So f is positive. So yes, f is positive. It's continuous because you should know that 1 over x looks like this, and 1 over x plus 1, 1 over x plus 1, it equals 0, the bottom, equals 0 and negative 1. That is, we're going to draw it as if their origin is right here. Those are the new axes. We'll draw the same graph. And yeah, this portion is continuous. You're only going to have trouble on negative 1. It's continuous from 1 on. Okay, so it's continuous. Now, is it decreasing? Depending upon how insane or rigorous your teacher wants to be, one can just say, well, look at the graph. It's decreasing from 1. Just from 1. Just from 1. It may be increasing elsewhere. We don't care. But from 1 to infinity, it's decreasing. It's going down. Okay, so it lived up to this 3 criteria. The function for x greater than or equal to 1 was positive, it was continuous, and it was decreasing. So now we can go ahead and use this theorem. Okay, don't be tricked. Or, don't be tricked into using it. You want your teacher to give you a problem where he or she says, use an integral test to show the divergence or convergence of this series. And you want the series to be increasing. Then you can say, f of x equals this function, which is increasing. We can't use the test. Thank you for the 10 points. Okay. Suppose you have, I don't know, here, you have 1/2 plus a fifth plus a tenth plus a 17th plus a 26th, etc. I see 5 times 2 is 10, but 10 times 2 is not 17. I mean, you can stop there, but 17 times 2 is not 26. We're not multiplying. Well, first we're adding 3, and then we add 5, and then we add 7, then we add 9. 3, 5, 7, and 9. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. 5, 7, 9. And 1 squared is 1, 3. 3, 5, 7, and 9. That's just what we have. These are exponents. You need to see that pattern. 3, 5, 7, 9. Those come from pallets. The bottom is 1 over 1 squared, which is 1, but I want 2. So I add 1. 1 over 2 squared, that's 4, but I want 5. So I add 1. I'm always going to add 1. 1 over 3 squared is 9. Add 1. That's 10. And so on. And so on. Okay. So A sub n is 1. Now, write down the stuff that doesn't change. The 1 is in all of them. The 1 is in all of them. The division line is in all of them. The power 2 is in all of them. And they all have the plus 1. What's changing is the base of that power 2. 1, 2, 3, 4. Well, it's starting at 1. That is, when n is 1, it should be 1. The first term, it's 1. The second term, it's 2. The third term, the base is 3. So that's the sequence. That's what A sub n equals. Now, the question is, this top one, does it converge or diverge? Does it converge or diverge? That's what we want to know. And we're asked to use the integral test. So, we integrate from 1 to infinity this function, except instead of n's, we write x's. 1 over x squared plus 1 dx. But you know what? That's octan. That's octan of x. From 1, well, I can't write infinity, so I put the k, and then I have to write the limit as k goes to infinity. Okay. So now this becomes the limit as k goes to infinity, and I get the tan inverse of k. First I plug in k, minus, and then I plug in 1. Minus the tan inverse of 1. But what is the tan inverse of 1? The tangent of what angle gives you 1? Like 1 over 1, square root of 2, 45, 45. It's pi over 4. So this is equal to the limit as k goes to infinity of the tangent inverse of k minus this silly constant, pi over 4. So now, what's the tangent of what angle gives you k? If this is theta, this is asking the tangent of theta, tangent of what angle is k, where k is infinity. Okay, I think at this point one should look at the tangent curve. The tangent curve goes like this, where this is negative pi over 2, and this is positive pi over 2. want to be sure. Yeah. Okay. So, you know, the tan inverse is supposed to be positive infinity. And it's positive at pi over 2. It's positive infinity at pi over 2. It's negative infinity at negative pi over 2. So it's pi over 2. The limit of this is pi over 2. And then we take pi over 4. Now, you can stop there. This is a real number. Half pi minus a quarter pi is a half pi. I mean, do the math. This is, if you want, this is 2 pi over 4 minus pi over 4, which is pi over 4. You see that you're getting an answer. It converged. That means it converged. So now I can come up to the top and say it too converges. Okay, this was a deep, deep problem. First you had to realize that this here, forever, I meant to include the 3 dots. This here was 1 over, the a sub n term was 1 over n squared plus 1. And then you had to know that this integral was the octan. And then you had to know the octan of positive infinity was pi over 2. You probably knew the octangent of 1. I mean, if you knew one of them, that was the easiest one to know. Okay, that was not the weakest link. Okay, so this was a hard problem, but get rid of it. I presented it to you. I'm not very up on these problems, to be honest, so I don't know which are easy, which are hard. Once I get into it, I say, oh, that's a hard one. This was a hard one. Now, what if you had a p-series? What if you had the summation of 1 over p to the n? What if you had 1 over the summation of p to the n? The summation of 1 over p to the n. Okay, how about we have 1 over the summation of n to the p? Does it converge? Does it diverge? Well, let's use an integral test. Instead of n, we write x. 1 over x to the p. And we have to integrate from 0 to 1. dx times dx. Well, the x to the p I can bring up like that, as x to the negative p dx, from 0 to 1. And remember, the rule for x to an integer, dx, well, you add 1 to the integer, and then you divide by that same number, plus the constant. Now, of course, you can't do this if the bottom is 0, and that's when n is negative 1. When n is negative 1, it's ln. Okay. So I add 1 to the power. You have negative p and you add 1, you get 1 minus p. And you divide by 1 minus p, and you go from 0 to 1. So, something's bizarre. Okay, so first you let x be 1. So you get 1 to the 1 minus p over 1 minus p minus, and now you let x be 0. Get 0 to the 1 minus p over 1 minus p. And of course now I see my big problem. I don't know why I'm going from 0 to 1, excuse me. I'm supposed to go from 1 to infinity. That's what the integral test dictates, that I go from 1 to infinity. go from 1 to infinity. I go from 1 to infinity. So what happens is it then becomes a limit as k goes to infinity of x to the 1 minus p over 1 minus p from 1 to k. So let's figure out what this is. But don't not write the limit in front. First you plug in k for x. You get k to the 1 minus p divided by 1 minus p minus, and then you plug 1 in. You get 1 to the 1 minus p, which is 1 over 1 minus p. This, and then you take the limit. The second term, 1 to the 1 minus p over 1 minus p, that's not going to change. Okay, so this becomes the limit as k goes to infinity of k to the 1 minus p over 1 minus p minus 1 to any power is 1 over 1 minus p. And the limit of that isn't affected. The limit of this constant is just itself. It's the first bracket that we're worrying about, and I have no idea why the word limit didn't come up. Now, if this power is more than 1, k, a large number, raised to a positive power. If this power is positive, 1,000,000 to the third, a really large number. A billion to the fifth is a large number. 1,000,000,000 to the 50 is a large number. Okay, this diverges if 1 minus p is bigger than 0. Let me just come to the top for a moment. If 1 minus p is bigger than 0, add p to both sides. That says that 1 is bigger than p. There's one reason why 1 is bigger than p, and that's because p is less than 1. If p is less than 1, it diverges. Now, it will converge if this power is negative. Like suppose you have k to the negative 2 over 1 minus p. This will become 1 over k to the 2 times 1 minus p. And if k gets bigger and bigger and bigger, it goes to 0. If that power is negative, it converges if 1 minus p is less than 0. And that's going to happen when p is bigger than 1. Okay, that happens when p is bigger than 1. Well, what happens if p is 1? What happens if p is 1? Okay? What happens, so we're kind of done. We did 90% of this. We just need to finish up this one little problem area. What happens when p is exactly the number 1? And I decided to just give you the answer. It diverges if p is between 0 and 1. It diverges if p is in between 0 and 1. Okay. It diverges if p is in between 0 and 1. Okay. It converges if p is bigger than 1. It diverges if p is in between 0 and 1. Okay, that's the p-series test. Okay, now you can just work this out on your own. Not work out. You can do examples 1, 2, 3 with this rule in the bottom corner. Just know this simple rule, you're in business. So if they ask you the summation and then goes from 1 to infinity of, say, 1 over n to the third. Now, the reason they want n to be in the bottom, and if the power were negative, then n is really on the top, and they don't want that. They don't want to look at those examples. Well, this is a p-series test. Remember, the summation as n goes from 1 to infinity of 1 over n to the p, it diverges if n is between 0 and 1, p is between 0 and 1, and it converges if p is bigger than 1. Well, that's p. P is equal to 1/3. This implies p is equal to 1/3, which implies that p is in between 0 and 1, which implies it diverges. You just look at the p. You just look at p. This is your Bible right here, for the p-series. 1 over a summation from 1 to infinity of 1 over p. Just decide if p is bigger than 1 or not. If it's bigger than 1, it converges. If it's between 0 and 1, it diverges. So if you have the summation of 1 over the 5th root of n goes from 1 to infinity, just remember that the 5th root is n to the 1/5, this summation. This implies that p is equal to 1/5. That is, p is in between 0 and 1. It diverges. Next problem. Okay, there are p-series tests, beautiful tests, makes life easy. Okay. What if you have this problem? What if you have a problem that looks like this? 1 plus 1 over square root of 2 plus 1 over square root of 3 plus 1 over square root of 4, etc. Remember, the first one is 1 over square root of 1. Well, this is the summation of 1 over n to the half. Remember, square root means half, as n goes from 1 to infinity. If n is 1, you get the square root of 1 first. And if n is 2, you get 2 to the half in the bottom, which is square root of 2. Then you get 1 on top always. The bottom square root of 3 is our 3 to the half. The square root of 4 is 4 to the half. This is it right here. So, this implies that p is a half. And if p is between 0 and 1, including 1, it diverges. You have the summation of 1 over n to the 1.031, that then goes from 1 to infinity. This implies that p is 1.031, it's bigger than 1, which implies it converges, the p-series. It has to be of the form. Everything that you see in red must be there. The summation as n goes from 1 to infinity of 1 over n, that must be there. Well, and p must be there, a number. And it all depends on the p. It all depends upon what p is. Does this diverge or converge? What if you have the summation of 1 over 2 to the n minus 1? Okay, what if you have that? Now, we know that the summation of 1 over n to the p, if p is 1, that is p is 1, that if p is 1, it diverges. Okay? Now, if this here is bigger than 1 over n, for example, or any multiple of it, if this diverges, for example, if this diverges, that implies that half of it diverges. But half of it is the summation of 1 over 2 to the n. Okay? So if this is bigger than a divergent series, it too must diverge. It's bigger. This is bigger than the summation of 1 over 2 to the n. This denominator is bigger. It's 1 bigger than this. The numerators are both 1. On the right side, I'm dividing by bigger. On the left side, I'm dividing by smaller. The left side is bigger. This is bigger. But this is equal to factoring out the 2 summation of 1 over n. But this diverges by the p-series test. This diverges. It diverges with p equals 1. So half of infinity is still infinity. You can't multiply infinity by any real number and not get infinity. Unless you multiply by a negative number and you get negative infinity. Although, you really should stay away from 0, okay? Three times infinity is infinity. What if you have this one? What if you have the summation as n goes from 1 to infinity of 1 over n squared minus 1 over, say, n cubed? Now, this does equal the summation as n goes from 1 to infinity. Now, whether you write down what I am writing down right now or not, you should definitely be thinking it. You think that. Now, the problem is that, well, they both converge because p is bigger than 1. Okay, they both converge. And converge minus converge converges. Maybe this converges to 7.2 and this converges to 3.8. Well, the difference is going to be a real number. The difference isn't suddenly going to be infinity. They say, yes, that converges. By the p-series test where p was bigger than 1. Okay, that finishes the integral test and the p-series.